In this video, we are going to talk about EMC and how to fix it. We are going to talk especially about power supplies. On the left, you can see what we have before, and on the right, there is the graph. These are the results, what we will create in this video. We will design the filter for this power supply. You will learn how to do it, how to calculate the components, and Thomas is going to explain everything. Is this what we are going to talk about, Thomas?
Yes, that's right, Robert.
Okay, and you have like practical examples. So this is not only theory, we really have this circuit, you are going to measure it. So if someone is interested to learn how to measure EMC in their lab, they can basically follow what you will be doing. And as I said, you have a really cool method how to calculate this filter. So we will do it. We will implement the filter physically, and then we will measure it again. And also you will explain a lot of background, so everyone can understand what the problem is, and also not only how to calculate the filters.
Yes, I try my best.
Okay, so let's start. Where should we start?
Where should we start? I would say from the beginning.
Okay, okay. Show what kind of setup we have. So what is the power supply? What we are going to fix, and something like this.
Okay. Yeah, just imagine you have a power supply like this, and you later on want to sell it. Then you have to make the EMC test, sure. And there's also one test where you're measuring the interference on the line. And this is as normally done here with such a AC listen. You have a spectrum analyzer here. There is some DC load where you waste all the energy here just to run the circuit. And especially here you have an isolating transformer so that the protection circuit does not turn off your AC supply. And
yeah, go ahead.
And today, because this is high voltage, we will go to a DC measurement, which is quite similar. So we have also here our device on the test. We have again here some decoupling. Here is a DC load. And again here listen, but this is now a different one. This is now for the DC supply. And here's something special on this measurement. Here we have this listen mate, where we can also distinguish between if it is a differential or a common mode interference.
So basically, in the middle of the red board, that's the power supply what we need to fix. Or first we are going to measure it and then we will fix it, correct?
Yeah, yes. So this, our device on the test looks like this here. It is a very simple buck converter. So you can see the circuitry on the left side here. We have this big coil, which is here the black one. We have the output capacitor. We have an input capacitor, and the black one here, this is the diode. And yeah, the big IC which you can see here, this is actually the switch. And this creates now out of 12 volts a 5 volt at the output.
What is the current for the output?
Yeah, this depends in which range you use it. I have at the moment, I think it's about 1 ampere, but this is not the limit which we actually have here.
Okay. And so what is wrong with this board? Because this looks like some kind of board what anyone would design, yeah?
Yeah, for this, I have to go one step back and look at the basic design of such a buck converter. And this is, so when you open and close the switch, you can then create a low voltage at the output. And the two kind of current flows you can see here. So when the switch is closed, you have this red line number 1. And when it is open, you have the second one. And now you can see at certain points two lines here. These are the places of the current where it does not change very fast. The difference here on the diode is you have only one line, and this means at one switching state it is on, and on the other one it is completely off, and therefore you have a very hot slope. And this slope is on 4 different places. It's here over the transistor, over the diode. Then here you can also see here's also only one line. So this is then the hot loop. The hot loop is this area where the current is changing a lot, and therefore when you change the current over a part of the line, then it is induction which you will get. Every piece of line you have is a short inductor, and when you change the current very fast over an inductor, you get a voltage drop.
Okay, can we go back to the previous slide? This is very interesting way to look at the circuit. So basically, everywhere where the two lines are, it means there will be kind of constant current.
Yes.
So these are the parts which are not like as critical as the parts of the circuits where are only one lines.
This is right.
Okay.
For the current itself, it is not critical. So the output capacitor here, it is actually not a problem. You have even the current in the same direction. I mean, it looks like a triangle, but it's not switched very hard.
It's not like from 0 to full voltage and from full voltage to 0.
Exactly. And when you have not a very fast current change, then also the inductance will not create a lot of voltage drop over there. But here over this components, you will have the voltage drop. Sure, here over the diode, I mean, what you cannot see here, which we'll talk later on, here's the switching node. This is also a second point, which is important. But yeah, you have here this part over the ground. So some people, when they don't pay much attention, create here also a high inductance, and then they create already a lot of common mode noise. And here on the input capacitor, we have the same. We have also a very hard switching, and here this fast current change goes now over the capacitor and also over its parasitics. And this will then create a differential mode. And this is also what we see at the beginning here. This is our circuit which we have. And we have only here this capacitor and the input. And we have no additional filtering element, so that all the interference which is here created with the current will then go out to the left to the voltage source.
Okay, I have a couple of questions. So can we go to the previous slide? Yeah. So first, I would like to repeat what you just part of what you just said. So basically, when we have these high currents which are changing very quickly, it means and if there is an inductor, then on this inductor we will lose some voltage, and higher the current is, more voltage we will lose, and also faster this changes. That's also important. Yeah.
Yes.
And so why? Okay, we will lose the voltage. So this could be problem. We go out of the range of working of the power supply or something. But why this is problem for EMC?
So the source of the EMC is actually on this capacitor. So the interference source. You will get here this voltage drop. And now this is a certain amount of power which is created. And it goes in both directions. So it's going in this direction when you look at it as a RF point of view, and also on the other direction, which means a certain amount of energy is now traveling between the upper and the lower line and goes to the source backward. And then you have over the source itself a current, which is then going here over the plus, over the source, and then back over the minus. And then it will or it can interfere other devices, which also require a very quiet supply.
Okay, I understand. So because in specific point we lowered the voltage, this change will kind of spread in all the directions which are connected to this point, and this is what will actually make the EMC problems, because that's the kind of field or energy change traveling through circuit and lines and cables and everything.
Yeah, right.
Okay. And you mentioned something like common and differential. We will explain this a little bit later, correct? Do you have some demonstration? So if someone doesn't understand right now what this common mean, what this differential means, you will explain this. Okay. Okay, so we understand where the problem is. What do you have on the next picture?
So let me see. Let's maybe go to that one. So we now understand that we have this voltage drop over this capacitor, and now we need some kind of filtering, which means we want to reduce this voltage drop over this blocking capacitor by creating a voltage divider. And this is now for the high frequencies, first an inductor, which is a high impedance, and after that a small impedance, which is a capacitor. And this voltage drop, which is at the beginning A over CB, is now reduced, and then you have at the terminals here much lower noise.
So basically the voltage drop or the noise will not travel behind our filter.
No.
Okay.
Because the impedance, which is seen here, is first very high, which is already, let's say, the noisy voltage will stay here. And in addition, you have here this division ratio, which we will later on see in the picture very, very good. And this will very easy divide your voltage.
Okay. Okay.
But it looks in the first picture very easy, but in the reality, and this is actually the main point of EMC, you have always the parasitics, which means everything which you have on the schematic is in the layout a little bit more, let's say. And when you have an inductor, you have always a stray capacity, which is between the windings. You know, when you have something like two plates, it is like you have two different lines side by side, and this is like a capacitor. And so for high frequencies, it's just passing over the inductor. And also for high frequencies, such a capacitor is actually not a capacitor anymore, it's an inductor, because the inductive part of the capacitor has now a higher impedance than the capacitor itself, which means at high frequencies, and by high, I mean somewhere between, let's say, starts from 10 to 100 megahertz, or depending on the components, you see only here a capacitor and an inductor. And then you have this voltage divider by this capacitor and here inductor, and here it goes in the other way around. So everything which you are filtering here with the normal components will then be reduced, and after a certain frequency again you have no filtering effect at all. Yeah.
Yeah, I understand this. When we see the graph, then I think everyone will understand.
Okay. Shall we already go to the wallpaper?
I would show some measurement. Can we see some measurements before we move to filters?
Sure. let's maybe start here with the setup. I will
Oh, we
change
can talk a
now.
little bit about this setup. Uh,
Yeah.
so you mentioned this listen. What exactly this device is doing? Listen. What does it mean? Listen.
Listen is a line impedance stabilization network, which means in the inside it looks like this. So this one here, which I have on the table, is actually not a simple listen, it's a dual listen. So it has two listens inside. In the end, it's very simple. It's again this 5 microhenry inductor, which should represent 5-meter line, because 1 nanohenry is about approximately 1 millimeter as a line, and so you are here, let's say, simulating 5-meter lines.
Oh, so one is 1 meter, 1 millimeter, because
One
you say
microhenry is
millimeter.
approximately 1 meter, but
Okay.
only when the return path is far away.
Okay.
When it comes closer, the inductance change.
Okay.
Yeah, and here we have this 220 nanofarad, which should be representing a short. So all the voltage which is here on the input, by input I mean here one of these colorful inputs. When you have a RF there, it will drop over the inductor, and then it goes out here to this measurement port.
So why do we need this? That's the main question. Why do we need this?
With that, you can measure the RF on the line, which means all the noise which is between the line and ground. Ground is here the metal plate, which is on the lower side. It should represent our complete environment.
So we need this device for the measurements. You can't measure directly on the lines. Yeah.
No, you cannot do that because you will change the impedance, and depending on what kind of setup you have, you would measure every time something different. And so the people decided to have a certain setup, and they are measuring all over this certain setup, and they will get all the same results.
So basically, if someone would like to measure power supplies, they may need to buy this kind of device.
Right, or they can build it on their own.
Okay.
Yeah, and this is also in the regulations. You can read what special requirements there are, and when you fulfill them, you can also use them. Good. In the end, here, when you are not measuring one of the lines, you have to terminate them with 50 ohms, so that you are again measuring all the time the same, because the RF, when it goes to the inside, it will see here this high impedance, and when you don't connect the 50 ohm, you will actually see here this high impedance, and in the other way around, you have this 50 ohms. Maybe later on, let's go to these two values again to see why they have chosen these values, and also this one here can also be explained with the RF wallpaper.
Okay. Why it says RF? What does it mean, RF?
This one here.
Yeah, I mean like RF. They use it also on the outputs. RF plus, RF minus. What does it mean, RF?
Yeah. The listen, so it has one side which is connected to the power supply, and here you have no RF frequency. So all the RF frequency which goes here to the inside will not go here to the outside.
So the RF frequencies, that's where our possible noise will be located.
Yes.
Okay.
So here you have your noisy device on the test, and RF can now be between the lines.
That's why it says DC
ground.
plus RF, and then you only separate the RF. Okay, I understand now.
Yeah. So you can have on plus and minus RF compared to ground. And this compared to ground is now here on the output. And this is let's say the real test in the end. You are measuring one output here, which is the plus compared to ground, and then the other one. So then you switch here to 50 ohms and measure the other port.
So RF plus is basically the plus voltage, and RF minus is the minus voltage.
Minus.
Okay.
Yes.
I didn't want to say ground.
Yeah. But actually, here with this one here, you can say this is the reference.
Okay.
And with reference, you can also use it as ground. You know, ground has two functions always.
Which one?
It is once the reference, and the other one is the equalization of the current.
Okay.
And because these two functions compete to each other, the people have always problem with round and also to name them.
Okay, let's go back to the picture. So what else is in your setup on page number 4?
Here,
So there is
what we saw
the
before,
DMCM. So what does it do? DMCM, listen, tech box.
this one here.
Yeah.
This one means differential mode, and the other one common mode. So when you have these two lines, which are now measuring from minus and to ground and plus to ground, you can now add them, or you subtract them. And when you add them, you are measuring the common mode. And when you look for the difference, so what is the voltage between these two, this is then the differential mode.
Okay, so I understand. So I think this is what is very important to explain. So this differential, that's the kind of noise between plus and minus, yeah?
Right.
And the common mode is then the difference between the plus and the big ground plane, or minus and the ground plane, or?
Yes. So here you can see it also with the currents. So the differential mode, because you have, let's say, a bad differential mode blocking, the current goes also over the listen here. You will get the voltage drop over the coil. Then it goes over the ground here to the other one, and here backward. Or let's say in the end, when you have here the 50 ohms, you're measuring it over the 50 ohms. And the current goes here in and here out. And for common mode, you have a current which is going over the capacitive tray of the device. So the device itself has, let's say, some noisy point. Noisy means a very fast slope. You have the capacitive tray to the outside, and here you get the current over the ground.
So the common mode measurement is measuring the current through this ground.
Yes.
Okay.
It's the sum of the ground current here, and you're measuring it by measuring the current also over the wires.
So this is very important, because I think many people may think all the currents only flow through the wires which are connected to your power supply, but that's not true.
Currents go always in circles, always, even when you make an ESD test.
Okay, so that's also why we need this big metal plane, so we can do the correct measurement. When you go back to your picture, so everyone who is doing this kind of measurement, they also need this big ground plane. This.
Yes.
Okay.
This is, let's say, the reference to the outside. And here, this listen has a metallic bottom side, which is touching the ground. It's very important, so that, let's say, the current which goes from here over the capacitive tray to this ground plane, it goes back here and then over the listen and over the lines back to the circuit.
This was actually my tricky question. Like, I wanted to surprise you. Like, so how these currents from our PCB will actually flow through this big metal plate, but you just explained basically through air.
And it's actually going always with the path of the lowest impedance, which means, it's actually going as close as possible under the lines. So that you are minimizing the inductance. This is always what the current is doing.
Okay, so is it important how you place this device during your measurement? Because I see you have it placed on a box and then cables are basically lying on the metal plate. So is this important how you place it?
Yeah, it's also described in the regulations, what is the distance to the ground, because when you change the distance, you change also the capacity, and then you change the result. But this setup here, which you can see, is only a pre-compliance measurement. You can see it here on the spectrum analyzer. As normal, you need a receiver here, which has the real detector inside and all the filtering stuff. But on the workbench for a developer, this is a good setup to, let's say, reduce the noise.
Because
And
you
then
see
you go
if
to
there
the
are any problems, and you can also see the changes what you are doing, and how much these changes were.
Yeah, you
Okay.
save a lot of time.
And I think what we did, sometimes you get results from kind of preliminary measurements in a real test house, and then you have some kind of absolute values, and then when you make this kind of setup, you can actually, you should get same kind of graph or waves, but maybe relative to the measurements what you got from the test house, so you know actually how much you are you need to reduce your noise.
You should actually measure the same here.
Same.
This is a good setup where you can have the same result in the on your own place compared to the EMC chamber.
Cool.
It should be actually the same when you make no mistakes on the setup.
Okay, that's interesting. And so okay, sorry. So is not problem if these cables are lying on the plate?
Which one?
From the board connected to the listen.
This one here?
Yeah.
Yeah, this has to have a certain length. But here for our test, I need a little bit, let's say, more flexible setup so that we can change something and to test something. And therefore, I pressed everything together so that it can fit the camera.
But
so in reality,
so they're supposed to lie on the metal plate.
No, they have to go directly on here this isolation over a certain distance.
Okay.
But yeah, here for this demonstration, it's sufficient.
Okay. Okay. So then there is the DC load, so we can simulate the load of the power supply, and then we need spectrum analyzer. Do we need like some kind of special spectrum analyzer, or what is important for the spectrum analyzer to do this kind of measurement?
Important is that you're not missing signals. The most common mistake people do is when they're measuring, they have a certain amount of points in such a frequency range. And when this, let's say you make steps of 100 kilohertz, just as an example, and you have a filter bandwidth of 9 kilohertz, then you see not the signals which are in between. So for your pre-compliance, the first thing you need is an option, let's say, where your device is not missing the signals which are in between. Then you need a certain filter bandwidth, which is then the same as in the lab. And there are different kind of detectors inside. And yeah, the most important are the average one, the average detector, which looks just at the average of the signal, and the quasi-peak detector. But the quasi-peak detector take, let's say, a lot of time until he's measuring 1 point, because the filter inside takes a while until it is swinging in, let's say. And the quasi-peak should actually represent the ear of a human. And so you would recognize it when it is over a certain limit as in the audio region as something annoying. And I'm measuring here with the peak detector, and here I measure always the highest value. So it's measuring a certain amount of points, and then it takes the highest value.
Mm-hmm. Okay, can we do some kind of measurement? Do you have this set up?
Yeah. I changed the camera. Here is the setup. And for the first measurement, I actually removed this one here.
Mm-hmm.
So what we have here is
Oh, you have also the you don't have the filter connected right now, correct? You have because it's...
no, here, let me go down a little bit. Here we have the device under test.
Mm-hmm.
And here I have directly connected it at the beginning. I just placed it there on the breadboard so that we can go very quickly over this design.
Yeah, okay.
And yeah, then I have here the listen.
Mm-hmm.
And the one output is now connected with 50 ohm termination,
Mm-hmm.
and the other one goes into the spectrum analyzer.
Mm-hmm.
And here I have also a picture. Let me just show. Yeah, this is what we can see
So
as
right
an
now we are
interference.
measuring the common or differential?
Both.
Both, okay.
Because we are at the moment, we have this measurement set up.
Mm-hmm.
And we are measuring common and differential mode because we are measuring at the moment the plus line.
Mm-hmm.
And so it's always a summary of both. So you don't know is it the common or differential mode.
Mm-hmm. So basically we will see the maximums from both, but problem is if we would like to solve this kind of problem, we would like to know if the peaks are from the common or from the differential, and
Right.
that's why we also need the other device to be able to separate them. But right now we would like to just see if there is a problem.
Right. And to have a fast measurement, I have here now this peak measurement, and peak is always higher than the quasi-peak. And so when we fulfill this limit, then we will also have the quasi-peak limit.
Okay, and now the blue line are the limits.
This is now a limit for AC measurement, because you can also imagine you have the switching regulator in the front of let's say a rectifier and some transformer. And yeah, a transformer is actually at high frequency just a pause. So it can very easy go over the transformer without any attenuation. And so actually for testing, and when you don't want to have this high voltage directly on your table, you can start with that. Good. Yeah, and our goal is now to go, yeah, let's say beyond or under the limit here.
Okay, so the power supply right now, it's not good because the yellow is above the blue line, and we would like to make it nicer.
Yeah, that's right. And also, when I place it side by side, and now we can maybe see if there's an influence when I touch the circuit. So do we see an influence? Here maybe a little bit. And when you touch the circuit and it is changing, then it is a little bit a hint that you have a common mode also, a common mode problem on the board. But when you touch it, so let's say like this, and nothing is changing, then it's very likely that it is a differential mode problem you have. Because when you touch it, current goes over your body to the metal plate again, and this is actually what common mode makes, which makes the interference of the common mode larger. Good. This is now the first side. Maybe let's measure also the other side and compare both. So I can hold this one here.
So you are going to measure the minus now, correct?
Yes.
Okay.
Let's see if there's difference. What do you think, Robert?
You say you are measuring both, so there should not be difference.
Yes, you're right.
Okay.
It's actually very similar, and this is often the case. And yeah, here we see the same result. And in the next step, we want to distinguish if it is a differential or a common mode interferer. And for that, I will now place this device here in between. So I have the plus line, which goes into the first one, and the other one goes in listen number 2. And then, yeah, we just attenuate the output of the common mode, and I connect here the differential mode. And now we see, it's also a little bit higher. And the reason for that is to correct the measurement, because you're adding them. And when you calculate it with math, you have to add here a 3 dB correction also. And then it is the same again. In
Because
the
there is
differential mode.
3 dB in the device, yeah?
Yeah, you are adding 2 times the differential mode, and this is actually then 3 dB more power. Yeah, and I think the device itself has also some attenuation, and also take care about the listen. It has on the output a 10 dB attenuation, which means you have also to introduce it on the device as an additional attenuation. Otherwise, your measurement would not be correct.
Okay.
But this is also an advantage because of this attenuation. My device here on the input is not in such a big danger, because when you don't have this attenuation here, this means also strong interferers can directly go into the device.
And it can damage your analyzer.
And you can also add your limiter for additional, let's say, security. But here in my setup, I have no big interferers, so this 10 dB would be enough.
Okay, so now you are measuring the differential mode?
Yes, this is now differential mode.
So does it mean the noise what we have is mostly differential?
It's actually only differential mode, yes.
Okay. Oh, that's why there was no change when you were touching the PCB.
Yes.
Okay.
Let's maybe also have a look at the common mode.
Yeah, I'm curious.
So I changed this one here to the other connection, and this is what we have at common mode. So, I can also add here the preamplifier to get a little bit more sensitivity. And yeah, you see it's much less common mode than you have differential mode. And now let me show you what happens when I touch the circuit. This is what we saw when I was touching the circuit. Here at a certain frequency, it changed because the common mode comes a little bit higher.
Okay, so basically what this means? This means we have to filter the wires which are going out of the PCB because the noise is between them.
Right. So at the moment, go one step back here, we have the problem that the current is now going here to listen and then over the other line back. So we have this RF voltage drop here between the lines. And especially when you have these lines, let's say not close to each other, but spread like this, then you will have an antenna, and this can also radiate.
So basically, when you have power supply, it's better if the wires are closer?
It's always better when the both directions of the current are close together, because the emission itself, so the creation of electromagnetic wave, is a change in the current. So when you have a load and you accelerate it, you will have electromagnetic wave. And when you have one which is very close and in the other direction, it will create the same wave. Yeah, exactly. They will cancel each other out. And this is the reason why they have to be close to each other.
Okay, so how do we fix this?
We can now fix this with a filter.
Okay, now the interesting part, how to design this filter.
Yes. And for filtering, yeah, let's say I have a little bit a special method because I'm lazy. And on my side,
simulations.
I later on maybe, but for the first estimation, I have always my RF wallpaper on my side. It's the best EMC tool you can have. And I will show you now how you can calculate with this.
If someone would like to use this, can they download it from internet, or?
You can download it from my website.
From your website.
I created this. It's not my invention, but I drawed it in LaTeX. Took me
where you have it. First show what is it, and then we will show where people can download it. So let's have a look what this special paper is and what it can do. What this can do.
Yeah, the RF wallpaper is a logarithmic table in 4 directions, which means you have in the x direction you have the frequency. So it's going from 1 Hertz to 10 gigahertz. So it's covering, I would say, everything which is important. And on the y-axis, you have the impedance reaching from 10 milliohms up to 1 mega ohm. So basically also everything what you need. And now here is coming the interesting part. You can have also inductance and capacitor inside. And yeah, let's maybe start with such a 10 microhenry.
Before we go there, I have one question. Because I see on the impedance side there are also some inductance, no?
Yeah. But they are written in from the left lower side.
Okay. It's
right
basically the X continues. Okay, I understand.
Yeah, they belong to these lines here.
Okay, I
always
understand.
in the direction where it is written, you have to read it.
Okay, I understand now.
So here for the 10 microhenry, you have this kind of line.
What does it mean?
It means, so let me maybe see if I can use here this one. So when you go up here, you see how the impedance change over the frequency. So let's choose, for example, a 1 megahertz, which is here. You're going down, and at this point where you're hitting the 10 microhenry, you can then go to the left side and read the value.
So then 10 microhenry for 1 megahertz will have, let's say, I don't know, 50 ohms.
Yeah, exactly. A little bit more. It's about 60 to 70. And in EMC, it's actually not so important to have accurate values here. When you are in the region, I would say factor of 2, 3, or not factor 3, but let's say in this area here, it's sufficient.
And same for capacitors, I guess. So for specific frequency and specific capacity, you can see what will be the impedance.
Yes, but now you read it in the other direction here. And for 100 nanofarad, let's say you would use it for audio applications. So somewhere here, 1 kilohertz. Let's say for blocking, you will very fast see that this is actually a very high impedance, and the capacity is too low. But actually, now from this point, someone can say, okay, for this I use the calculator. But this is only the beginning. So can you already imagine, or do you have an idea what happens when this 10 microhenry inductor and this 10 nanofarad capacitor come together at this point?
Don't know, resonance, I don't know.
Yes, that's it. Here you have the resonant frequency of these two, and this is about 150 kilohertz.
Mm-hmm.
And this will later on be also important for the filter design. And you can also read the quality factor, and let me demonstrate it here with a coil.
Okay.
So this is one coil which we will use later on. So yeah, it looks like this. From the data sheet, you can read these values. So I choose here these 3 points, and I draw them directly here inside. And then you see the RF wallpaper is nothing else than this impedance, which you can read in the data sheet.
Mm-hmm.
It has also here a logarithmic x and y scaling. And now you can have, with one look, all the parasitics. So you can see what is the capacity, because here on the data sheet, actually no one tells you what is the stray capacity. And with this one here, when you have this point, you go down. So it's the other way around of reading. And you see it's about 12 picofarad.
This is actually very interesting. I had no idea something like this exists.
It's also possible that you use the calculator here, but as said, I'm lazy. I have it on the side, I use my finger, and in 2 seconds I have the result. Next point, which is also very interesting, is this resonance frequency here, which you can see at this point. It's a little bit higher than the cut of these two lines, and the distance in between is the quality factor of the component. So also very important for
so higher the point will be, higher
yeah, and this point is actually then this resistor. And as higher this point, as less losses you have in the core. But it's always good to have a little bit losses here, because otherwise you have this resonance circuit here inside, this one here.
So higher the R is, then higher the quality factor is, or lower?
Higher. As higher. Here actually you let's imagine the line would go like this. Let me choose a different color because.
And higher quality factor, it means it's more likely to resonate.
Yes.
Okay.
So let's assume it would be like this. So you have as normal the cutting point here, and here is your point. So you make the ratio of these two values, and you're getting the quality factor.
Okay. So because this was one of my questions, what I had in my head, like in the first slide we were like, oh, this is capacitor, this is inductor, and I was like, but real capacitor, it's capacitor and inductor. So basically, for real components, you connect this capacitor and inductor of the model or something, or a real component, and then you get real graph of the real component.
Yeah.
Okay.
Right. So when you make let's say a SPICE simulation, you will get the same result. It's completely the same. The only difference is here draw it, and on SPICE you simulate it. But the advantage of using this method will come a little bit later.
Okay.
But when you have now this on the RF wallpaper, you can also measure it with the network analyzer.
Okay.
So this is this component now. So when you're measuring the impedance, you can get this from from the network analyzer. Do you like to show you how this is measured?
Yeah, we can.
Okay,
we can show this.
Then I switch back to my camera. So And I changed the place a little bit. So here I have this network analyzer. You calibrate it to these tips here. And then it's quite simple. You connect a component. Come.
So basically, it's always good to measure real components.
You can also use the data sheet, but sometimes when I'm measuring,
you already have the
filters,
expensive setup, so why not use it?
Yeah, I mean, it's actually they become cheaper and cheaper, and it's not so expensive anymore.
So which one do you have, or which one would you recommend, like a cheaper setup?
Here, it depends on what you want to do. When you just want to make it, let's say, for your hobby, and you don't want to spend a lot of money, then a nano VNA is good. When you want to do it a little bit more professional, then I have this Siegland, what was it again? It's an A5002. It has 2 ports. And then, yeah, it's simply a little bit more professional.
Okay, so what do we see here? So you connected the inductor.
Yeah, this is now the inductor, and at lower frequencies. And you can now actually see it is like the RF wallpaper. You have here the impedance, and the frequency it's going from 10 kilohertz up to 200 megahertz. The power which is used here is actually quite low at the moment because I added also some limiters there. And so this is also the reason why you see here more noise. But the 3 lines are, the yellow one is the impedance. So it is always the highest value. Then the next one, this is this violet one. This is the imaginary part of the component. So it can be either inductive or capacitive. And the blue one are the losses. So here you can see actually the losses of the core over frequency. Yeah, and here it's going up as an inductor. Then here we have the resonance frequency of the core. And then here it goes down with the capacity. And with the setup I made here, so with these tips, my measurement is valid to about 100 to 200 megahertz. And then the change of the connection itself will have a big influence to the calibration. So up to this frequency range, I can very easily use it. And let's maybe see if there is a change when I touch now the core. You see it's getting a little bit lower. This is because the capacity is now a little bit higher between the windings. Yep.
You can see like the inductive part is it still has the same slope, but the capacity goes a little bit differently.
Yeah, exactly. So I'm not changing the inductor much. In this example, also the lines here have no influence because we have an inductor with a value, let's see, of, what was it again? Of 140 microhenry. It is like 140 meters of line. So when you add there 2 centimeters, actually it doesn't matter. This would be an additional 20 nanohenry. So here it actually doesn't matter where you connect it, directly on the end or here in the middle. It's the same.
Okay, I understand.
So this would be this component, and here we can see it's becoming a capacitor above, where is it? This 100K, 1 mega, 2, 3, 4, about 5 megahertz. When we go beyond this point, then it's more like a capacitor. but this is not bad. It's okay. It's just the behavior of the component. And then we have as filter component also the second one, and this is now the electrolytic capacitor. And here we can also use the RF wallpaper. So first we start again with the capacitive value. It's going down in the impedance. And then here, can you imagine what that is?
That's the ESR.
Right, exactly. It's the ESR of this component. And then after a certain frequency, it's going up again with the inductance. And now this inductance is now, it depends where you're measuring. As said, when the return path is far away, then every millimeter is 1 nanohenry, which means this is about 9 nanohenry distance in the data sheet where they measured this one here. I have it also on my side.
Okay.
Here I measured it. So this is now this one here. And I think it's better when we do it in live.
Okay, yeah, let's do it.
So that you can actually see here the result. So let's put it side by side, like this. I hope I have here the correct capacitor, but we will see. So
nice red one. Who is doing these red capacitors? Only one company is doing them red, no?
Yeah, this is from Würth Electronic.
Oh, okay.
Yeah, and this one has also quite low ESR. And here you can also now see the limits of a measurement device because I need more power. I cannot see here this area. You see it is quite noisy, and this is not valid up to this point here.
It was actually my question, like why it is so noisy there.
Yeah, it's I'm sending there with a 0 dBm of power inside, and you're looking for the reflection. And
there is no reflection.
It's actually at this frequency, also the coupler inside, and also I have here, maybe you can see it, I have here the limiter. And this limiter is also to protect it a little bit. I mean, it's not perfect, but for ESD, so that I will not destroy my device. And the frequency range is here from 200 kilohertz upwards. And this means it is also like a capacitor, and therefore it makes here this measurement not so sensitive. So when I remove it, this one, and calibrate it again, I will get here better results.
I understand.
But here is, as normal, nothing special. You have here just the ESR. You see it at the blue line. We have about 220 milliohms. And now let's maybe check what our inductance is. So I go here to a point where this slope is already very straight. And I have here a value of 1.4 ohms at 10 megahertz. 1.4 ohms at 10 megahertz. So I have here this 10 megahertz. I have here 1.4, which is somewhere here in this region. And now you can go in this direction. And you see this is 10, then 20. Let's say this is now 25 nanohenry.
Because the leads are a little bit longer where you connected the capacitor.
Exactly. And this is also something what we change now.
Okay, let's do it. Yeah, I'm curious.
So now we have 1.4. Let's connect it a little bit closer now.
Maybe it's not shorted or something?
No, it's not shorted. This is due to the calibration. It is already in such a low ohmic region that you have an influence depending on how your connection lines are. You see, when I squeeze it a little bit, already the calibration is not valid anymore. But what you actually can see, it's much lower than before. So when I go a little bit higher, with a little bit more distance, let's make it like this. Now we have about 0.4, and before that we had an inductance of about, or an impedance of 1.4. So here, as shorter the line, as less inductive part you have.
This is even very nice demonstration, like how much inductance this short wire has.
Yeah, as said, the return path here is far away because it's actually on the other side, and this means every millimeter is about 1 nanohenry.
Okay, so
And
so what is something else here, or we are going to design the filter now?
now we are going to the filter.
Okay.
So we had also this one, and now we bring both together.
So we put everything together.
Yes, this we are using the inductor here in green, as we measured before, and then we have also this electrolytic capacitor here in red. And now the interesting part is when you are looking for the surface which is in between. So this is your filter region, and it's starting actually at this point here. From here on, your filter is starting to work. So in this lower frequency range, so when you're below of this region, you have no filter effect at all, because this inductor has very low impedance, and this is much higher, which means all the voltage drop from here just goes as before to the supply. And starting from here, you create this voltage divider ratio, and you see the difference between the two become always larger.
So it means better and better and better filtering.
Right. You can now actually see where's the best point of the filtering. So where do you think is this point?
9 megahertz. I don't know where is the 10 megahertz line. Which one is the 10 megahertz line?
Yeah.
Okay.
Or where do you think? Maybe here?
Where the peak is, no?
This one here?
Yeah.
Let's go down. Yeah, exactly here. Here, it's a very wide distance, and you can actually calculate the attenuation which you will get. So maybe let's start at the switching frequency of this circuit, which is at 55 kilohertz. And at this point here, we have 50 ohms for the inductor. So this is like 50 ohms. And the other one is like 0.2 ohms. And now the ratio between of these two values gives you about 48 dB attenuation. So you will attenuate in the spectrum this value. But we start here at 150 kilohertz from measuring, and here we have 150 ohms, and the other is 0.2, which gives us about 60 dB attenuation. And the best value is, as you said before, here at the resonant frequency, and here we have 81 dB attenuation. This is quite a lot.
And basically important is this filtering region is exactly in the region where we need to filter our power supply.
Yeah, in the moment we are looking in this frequency range from here.
That's where the problem is?
To here. This is where we have the most noise, because I go maybe one slide back. Where is this one picture here? Oh, it comes a little bit later. Here it is. this is actually the spectrum, what you have as noise. So this noise is created. This is the current which is going over the capacitor, and then you have this impedance of the capacitor, and when you multiply this one here with the impedance here, you get the voltage drop which you have at the output. And this is what we actually saw here. This was this one. And this is now attenuated with this filter.
Okay, so this is from what, 100 kilohertz?
This is from 150 kilohertz up to 30 megahertz.
And the problem is from 150 up to...
Yeah, it's actually starting a little bit earlier at the switching frequency, which we cannot see here. The switching frequency can be estimated also very easy here by these two lines. The difference is 55 kilohertz. And then you know, okay, there has to be an additional line here. But
Okay.
here we actually only need, let's say about 50 to 20 dB attenuation. This would be sufficient. But let's see what we have. So we have at this frequency, the 150K, 60 dB attenuation, which means, yeah, when we measure this with this filter now, it will be much better.
Okay.
And then actually it looks like this. So left side is without filter, and the right side is now with this filter, which we designed so far. And we actually cannot see it anymore because here we have about 75 dB. And when you now subtract this value, then you will very easily see it's about here 20 somewhere, yeah.
Can we also measure it? I'm curious.
But let me also demonstrate it, how it's looking like in a real measurement. I mean, this is now the picture, and
yeah, I would like to see it. Yeah.
So the proof.
Yeah.
In the end. So I have here the common mode, what you can see. Switch it back to differential mode.
Can you move the camera so we can see what you are doing? Oh, perfect. Yep. Thank you.
And I can also hear the analyzer, which says it's too much power. So at the moment, I'm here directly measuring on the output. And now we have here this coil. Oh, let me maybe remove this one here so that you can see it there. And the next thing is this capacitor. So I disconnect the power, and then I go here to this measurement stage and connect it again. And this is what we see. And here I can now add the preamplifier again, then it gets a little bit lower. And maybe now let's do some average. Maybe then we can see something. Now you can see now here, yeah, this one peak, and yeah, it looks actually quite good, but a real engineer would say it is over-engineered.
Because the components are expensive, or big? They are big.
Yeah, it depends. I would say the components are a little bit too large. You can also choose let's say the cheapest one.
Okay.
Now you look at the price table and choose the cheapest one. And the good thing
is... So this is just the first step, like we can fix it.
Yeah.
Okay.
So with this one, it is perfectly fine. Everything is wonderful. But now you can optimize. You can now make smaller parts and do all the engineering magic stuff. And here you can actually see what you can do.
Mm-hmm.
So let's say
Mm-hmm. So you put here
what
150 again, and based on how much dB we need, you can actually kind of come up with the capacitor and inductor.
yeah, what do you like to change? Let's say you're using a smaller capacitor would be a possible way. So I mean, here's the switching frequency somewhere
Oh,
here.
I don't see it.
It was at 55.
Ah,
So
okay, I
at
see
this
it now.
point.
Okay. Mm-hmm.
So you can now say, okay, the capacity can be a little bit lower in the value, but also the inductor can be much lower. I mean, we start our measurement here at 150K, which is here. And let's say we need only about let's say 20 dB. And every decade you have is a 20 dB. So here it would, for this you see 81. This is 1 decade, 2, 3, 4.
Mm-hmm.
And so here we actually only need 1 decade, which is then here at this point.
Mm-hmm.
And this means you can from here on go down and see a 2 microhenry would be also okay. But there is one thing which you have to take into account. But maybe let's first do this. Now, when you are using a 2 microhenry, then you would have this filtering region.
Mm-hmm.
And here you have about the 20 dB. So this electrolytic capacitor in combination with a smaller inductor would also be fine. But at this point, you have a resonant frequency because the capacitor and the inductor came
Okay,
together.
I understand.
And this should not be too close to the switching frequency.
Mm-hmm.
The baddest thing would be when you have, let's say, a ceramic capacitor, which came down here with a very low ESR, and you are hitting the inductor of the blocking exactly at the switching frequency.
Mm-hmm.
Then you are amplifying the noise in such a way that, yeah, your circuit can actually be damaged. I had a company, there was such a high current because of this effect that the coil itself was soldering out of the circuit.
Really?
Mhm.
So basically, it really is important what kind of capacitor you use in
Yeah,
this filter, because you can actually uh, kind of by accident you can create a filter which is resonating at the switching frequency, and then this is going to be a problem.
yes, this is right. And here you can see it very, very good. Let's say we are still using this inductor as it was before.
Okay.
Here you have the resonant frequency,
Mm-hmm.
and our switching frequency was here,
Mm-hmm.
so far away.
Mm-hmm.
Let's say the switching frequency would be here at 2 kilohertz. This would be a nightmare.
Mm-hmm.
The only limiting value for this resonant circuit here is the ESR.
Mm-hmm.
And when you have very low ESR, then yeah, you
I
get a
understand.
very
I understand. So basically, you are allowing very high currents flowing through. Mm-hmm.
yeah.
So that's why it may be useful to use electrolytic capacitor for filtering.
I would not say it's really necessary. The only thing is you have to pay attention
Okay.
here where it is.
So what would be better way to design, what kind of components to choose here?
Okay, yeah, let's see what we can do. Let me just remove this one here.
This is very visual actually to play with the filter.
Yeah, I mean, here you have it directly in front of you, and you can change everything. And in a simulation, you also can do it, but you have not all effects at once. Okay, let's just imagine we want to use ceramic capacitors.
Okay.
So which value do we use?
10 microfarad. I don't know. That's kind of the biggest one.
Yeah, the best capacitor value is when you are going into the ESR at the switching frequency,
Okay.
because then you have the maximum of the capacitor.
Mm-hmm.
So imagine here is your switching frequency, which is going down here. And let's say you have a 10 microfarad ceramic capacitor. It would go down here like this. But from here, it's going down with the ESR, which is approximately 40 to 50 milliohms in this area.
How do you know?
Experience.
Okay. So 10 microfarad ceramic capacitor would have...
maybe I have here something prepared for you, because I was expecting some questions which I don't have here directly on the slide. Here it is.
Okay, so the best would be actually maybe have a look on characteristic of different ceramic capacitors and then choose based on this.
Sorry, can you repeat the question?
So maybe the best would be to have a look at graphs of different ceramic capacitors and then choose based on this.
Yeah, I would say
that's what you have here.
They have almost, so here you can see this is the parasitic inductance of different sizes of capacitors, and this is the ESR. I extracted it from the S parameters of the vendor, and here it was Murata in this case. And here you can see over the frequency the losses.
I understand. Okay, so
and
lower.
When you use, let's say the 10 microns, you are somewhere here in this region. It's not exactly. It's also changing depending on what size you have and which material you have. But somewhere in this region, let's say below of the 100 milliohms but more than 10 milliohms. And this was the reason why I said 50 milliohms. Yeah.
So what does it mean? We would like to use something smaller capacitor?
Yeah, in this case, when you use a smaller capacitor, you have higher impedance here. But the ESR is almost the same. So when you use a 10 microfarad, the only way how you can reduce the ESR is to double the capacitors. So when you have not one but two, then you have the half of the ESR. And then when you have four, you have again the half of them. That's the only way how you can reduce the ESR.
But do we want to reduce ESR?
Here at the moment, it's not. It's limited by the capacity when you have a 10 microfarad. Here you would have also the 0.2, so the same value as the electrolytic capacitor. And when you look at this frequency again, where we want to attenuate, let's say 20 dB, then we would use here a 10 microhenry inductor. Would be sufficient. Here is then the resonance frequency, which is still below.
That's why we would like to use maybe 2 10 microfarad, because then it would go not 2. That would not be enough. It would move only a little bit.
Yeah, when we have 2 of them, then your line it's going down
20,
here,
yeah.
and also going down here, and also here the inductance is
a
little smaller.
Much. So what does it mean? What is the solution, the more optimal solution?
Pardon?
What is the more optimal solution?
So I would say when you have a ceramic capacitor, it's easier to handle, and you have also less current on the ESR, because current on the ESR means heat. heat means you have a chemical reaction, and then when you have a chemical reaction, your circuit is then, let's say, is not aging, or let's say it's aging more when you have a higher temperature. And when you have a ceramic capacitor, then you have here less ESR, less heat, and then it lasts longer.
Yeah, but the switching frequency or the resonance frequency is close to the switching frequency then.
Yeah, but it's still a certain distance here. So when this is, let's say, factor 3 in this region, then it's okay.
Ah, okay.
I mean, this tip here, this is like this, and then here it is already over the resonant frequency.
Okay, so it means you can use 10 microfarad or 20
Yeah.
microfarad.
Would be sufficient here. And this can be a, let's say, ceramic capacitor, and here, yeah, this may be also as SMD component, and then you have a cheap solution.
Okay, do you have something else here? So
yeah,
basically, this is the result of the video. So if someone would like to use these papers, they can use them, and they can design filters based on these papers. And we mentioned we would like to show where this paper can be downloaded. So you mentioned it's on your website?
It's on my website.
Okay,
yes.
can we go on your website?
Yeah.
So where this can be downloaded?
Is here.
It's
So
in German, yeah.
Yeah, it's in German. I have to also do it in English. It's some time. And actually here you find the downloads button, and then you can find it there.
Okay. So you can tell a little bit more about yourself when we are on your website. So what do you do? What's your job?
Yeah, I'm the guy who solves the problems of the people when they have EMC issues. So when you have a problem, then I give the people a consulting in online, or I drive to their site, and I also go into the companies and make some trainings, so that when they have a lot of people inside, they it's cheaper when all the people have the knowledge. And there I go with all my measurement equipment and experiments. Maybe you can see it also at the back. I have a lot of experiments. I go to them, and they get the theory and also the practical part.
So you have many examples, like this is when it is failing, this is how it looks when you fix it. Okay.
Yeah. And all the coupling effects, what is ground. And I also have in November in Regensburg, it's in Germany, always a training where the people can go there, and this is 4 days EMC and RF.
Do you have it on your website?
Yeah, it's.
And it will be in German, yeah.
This is in German, yes.
German, yeah, in Germany, but it is also in German.
I have also everything in English. But yeah, I can also go to English companies. It's not a problem. Only thing is I have the website now in German.
Okay.
Because yeah, this is new.
850. Here, so 850 for the 4 days per person. That's not expensive.
No, this is per day.
Per day. Okay.
And
Tag is day. I remember now my German.
This is it's 1 day, and it's not only me. I have 3 different other speakers also there, and yeah, they have all their special topics, and the people can then, you can maybe see it here a little bit, measure all the effects and see how they can get to a very good design.
And 850 is for everything. No, it's not only for your course, or also for the lectures of the other people, correct?
Yeah.
Okay.
Per day.
You know what I mean.
Yeah, it's per day. So
yeah, okay.
they are included here. So here, for example, my friend Manfred, or here is Marcus and
oh, and people can choose which
Melanie
day,
Klenner.
or it's 4 days. It has to be 4 days.
No, you can choose. It's here are the fundamentals, and here this is more when you're going into the PCB. So this is overall, so device. Then you go into more detail here. It's on the PCB. Then this day number 3 is for advanced designers, and the last day is only RF. So everything about differential mode lines, antennas, how antennas are working, and all RF components you can imagine.
You have one more really nice demo, if I remember right. Can we see it?
Which one? Yeah, right. Yeah, it's good for demonstrating the common and differential mode. And for this, I have to switch my camera.
Okay.
Yeah.
What do we see?
What you can see here is a setup of brick stones, and it should demonstrate the effect of common and differential mode. So you see here this thing which is moving inside. I hope you can see it.
Yes, yes.
This is your electronic, and here this springs which are on the ends. They demonstrate a capacitive coupling to the outside. And this, the wood, what you can see, this is the surrounding, means everywhere. It could be the metal plate of the measurement, it could be the roof, the wall, whatever. And here on this side, I have a little motor, and with that, I have connected here one line which is going to the outside. This is the minus. This is connected to the housing here. So this is the ground of the PCB, and the other line, this is then the plus line. And the differential mode which we had so far, it would be the same like this effect here. So you have one line which has a lot of noise, and then it goes to a source, and you're measuring actually here the differential mode. And when you have a lot of differential mode, you can maybe see it takes also the board with it, and then you get a certain amount of common mode also.
So common mode is when both are jumping?
Yeah, for common mode, I have also here something. There's a second motor inside.
Okay.
And here I can turn it on. So when you have no connection to the outside, I'm coming a little bit closer. Hopefully you can see it. You have no connection to the outside. The spring is not connected to the outside. This is a small capacitor, but when this capacitor is getting bigger, it is like when I connect it here to the surrounding. And the common mode looks then like this.
So basically,
it's getting
everything
more heavy. And this is then your circuit, which has this coupling to the outside. And you see it also at the lines here. And this is what you can measure as a common mode.
So in common mode, both will be jumping same way?
Yes, they're jumping in the same way because they have the reference as a board.
And in differential, they jumping different, or only one is jumping, for example, or different.
Yeah, exactly. Here you have only one, let's say. So it's like this. And for common mode, both are in the same direction. And when you have now a Y capacitor, this is often used in power multiplies as a stabilization to the housing, then it looks a little bit better. It's not moving so much as before, but it's still moving. And when you get to a certain resonance frequency, then you have again problems. Yep.
How did you come up with the idea to create this?
Pardon?
How did you come up with idea to create this?
The basic idea was the people was asking what is common mode, and then I started to explain it is like you have your board and you have springs to everywhere of the surrounding, and then there's one spring to the switching node which is then a little bit harder and it's pushing your board up and down, and then at a certain point I thought, okay, let's just do it because then people can memorize it better when they actually see it and have not only their imagination.
I definitely now memorized what is the difference. Really?
Okay, that's wonderful.
It really works. Okay, so did we go through everything?
I have maybe one interesting thing for you,
I'm curious.
if you like.
Yeah, definitely.
Okay. We did now this differential mode filter, and I want to show you this effect in the measurement when you are touching the switching node. So here I go back to clear right. And we have now, let me also show what I'm doing here. So, a little bit smaller here. So now we have this differential mode filter here, and the signal looks very good for differential mode. Now we can go to the common mode measurement. This is the other part. So I changed here to common mode. And you can actually at the moment see some noise, but this is the environment because as normal you need some shielding tent. And when I touch now, here I have a little tip, the switching node, it looks like this.
So now the common noise is bigger than the differential noise.
Yes, and I have for this also some copper foil, which is soldered here at this point, which creates a little bit more capacitive stray to the outside, and then it looks like this. And you see here now this is a common mode noise, and when I come close, you see it's already changing. I'm not even touching at the moment. I'm just hovering over that.
So basically this means using metal chassis is not always
Yeah, this
helping?
is yeah, it's helping because as normal you want to cool down your components, and your components are very often also the switching node. And when you come very close to the housing, you have this high capacitance in between. And this is the reason why the people later on need a capacitor back to the circuit when it is isolated. But here we have no common mode filtering at the moment, and therefore we have this kind of noise. And common mode filtering is actually very expensive. And yeah, but by design it is necessary to do it, and therefore the good thing here is now you can distinguish between common and differential mode. And also when I now measure in a different way, so as it was at the beginning, so we have here this connection, and this one is terminated. what we now see at the yellow is not the differential mode anymore, it's the common mode, and you can very easily see it when I come close with my hand. It's going up.
Again, because the differential is now
Yes.
very low.
Yep.
Okay, so about filtering the common mode, we can create another video, maybe if people
Yeah.
like this one.
Yeah, it was always take a while.
Okay, so if someone is interested to see similar video but on common mode, then leave comments, and maybe in future we will create another video with Thomas. But very quickly, we can just say, you mentioned already you would put capacitor between your circuit and metal chassis, for example. That's how you, one of
It's
the
not
ways how you can
everything.
do it, or not?
You have, well, maybe one last slide.
Okay, let's have a look.
This is how it is called, the last picture. So when you have a filter like this, so common mode choke, here are your Y capacitors, you get also problems here with resonance circuits within the circuit, which then can again create some weakness points. So it's not so easy at all to make a common mode.
Okay, that's why you mentioned it's not so easy. Okay.
Yeah.
Because you put more circuits together and they are going to influence each other, and you will have more resonance frequencies.
Exactly. This is very nice then. But from here we go into the simulation, as you can see. You can also see it as at the RF wallpaper, especially when you want to see what is the path here. It's very helpful. But then in combination with the simulation.
Okay, so again, if someone is interested about next video talking about this common mode, leave comments and maybe we will create it.
Okay.
Okay. Do you have any other slides what we would like to mention before we finish?
I think that's it for today.
So thank you very much, Thomas.
Yeah, you're welcome, Robert, and thank you very much for all your interesting questions. And yeah, hopefully see you soon.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedEval online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.